Hi everybody, welcome to our second lecture on computer animation. Today about 3D representation, three-dimensional. So first, the goal here is the representation of three-dimensional objects that can be processed by the computer. So how do we do that? There are different forms of representation of 3D shapes and objects. First, we have points and point clouds on the surface of those objects to describe those objects. Then we have lines and polygons. Basically, we connect those points with lines. Then we have splines, the so-called NURBS, and other curves, which means we have curved lines. So lines are straight, splines are curved, which is good for describing rounded surfaces. Then we have subdivision surfaces, which is basically another approach to obtain rounded surfaces. Then we have the manual creation of the representation. So we have geometric basic forms like spheres, cubes, cones, torus, etc. And we basically combine those basic forms into a bigger 3D object. Then we want to manipulate it, like changing size, aspect ratio, and so on. Then we have extrusion and geometry painting. So this is another way to obtain 3D objects from a 2D form, for instance. And then we have constructive solid geometry, for instance, Boolean operations, which is combining objects in a way that is described by those Boolean operations, AND, OR, XOR, and so on, as we will see. So first, some general aspects of representation forms. So for digital processing, we need sampling and quantization, and the achievable accuracy depends on the data format. For instance, single precision floating point, which uses 32 bits for the representation. So this is, for instance, used in VRML. This is a description of 3D objects. So we would represent, for instance, the position of those points with this accuracy. Yeah, then the attributes here are the information content, the approximation of reality, and also the processing costs. So let's start with the simplest representation, points and point clouds. This comes, for instance, out of laser scanners. We have a point. So when we have a point cloud, it consists of points, and each point is a simple vector, meaning we have our coordinate values x, y, and z. So each point is a three-value vector or three-value array. Yeah, it has no expansion, it's just a point. It also has no direction, it's just a point in space. So point clouds of surfaces can be approximated by a set of points which lie on the surface of the 3D object. There's no information about connectivity. So if, for instance, there's a gap in this surface, we might not see it when we have a sparse point cloud. And this comes, for instance, out of 3D laser scanners. Basically, we have a point of clouds. Sometimes we have outliers. So the point cloud might be more or less precise. And point clouds can be converted into other forms of representation, which require boundary conditions, for instance, when we have gaps in the surface, or treatment of outliers. So this is basically measurement noise, points which are not really belonging to the object. So here's an example. Here we have a mannequin, and we scan it with a laser scanner, for instance, and we have this point cloud. So each of those white dots is a point on the surface, and then we can process it and get, for instance, something like on the right side. So then we come to lines and polygons. Line is a straight connection between 2 points, and this is a description by means of the coordinates of the 2 points, which we call vertices. A polygon consists of at least 3 different points connected by lines. Right. So, and that's actually the most often used polygon, a triangle. So here in computer graphics we often have triangles. So the properties of polygons is they should be simple, no overlapping of polygon edges. If they are planar, all vertices are in one plane, and in triangles this is always the case. They are convex if all points on the connecting line between 2 vertices of the polygon are inside. This property is fulfilled if none of the angles between the 2 edges is greater than 180 degrees. And triangles always fulfill all 3 properties. Right, so you can see a few examples. So here we have a polygon which has overlapping edges. Right, so that's not a simple polygon. This is a simple polygon, but it's not convex because here this point goes inside the connecting line. So yeah. So when you connect those 2 points, then the connecting points are outside the object. So that means it's not convex. Here we have a convex polygon. All connecting points are inside or on this connecting line. Yeah, so because of simplicity, most often we use triangles. Yeah, so elements of polygons are the vertices. These are the corner points of the polygon or singular vertex. The edges are the edges of the polygon. The faces are the surfaces covered from the edges. So basically when we take the triangle, then the surface is basically the surface which is spanned by the edges. Then the surface normal is basically a normal which indicates the orientation of the polygon. This is usually determined by the cross product of the first 2 edges, and only for planar polygons unambiguously determinable, for instance triangles. And normally only the front side is visible during rendering, right? The one that is pointing towards the virtual camera. Yeah, so the polygon area is an arrangement of interconnected polygons, and we have limitations for computer graphics that an edge can belong to at most 2 polygons. Right? No vertex of a polygon may lie on the edge of another polygon. So again, this simplifies matters for the representation. Special feature here is a solid. This is a completely closed surface, like for instance in a sphere. And that means exactly 2 polygons belong to each edge. And we have a closed volume with clear inner and outer side. And between those solids, Boolean operations can be performed. For instance, constructive solid geometry, CSG. So this is actually what we will have most often in computer graphics. Some solid, a completely closed surface. Yeah, so here you can see a few examples. So here we have a sphere with different resolution, and you can see the more edges and vertices you have, the more round it becomes. Yeah, tessellation means a division of a surface into several subsurfaces which do not overlap in such a way that there are no gaps. Frequently we have triangulation, dividing into triangles. And the goal here is to divide a complex form into many simple forms. In computer graphics, this means the approximation of a polygon surface to the desired object. When we have a high polygon number, we get a good approximation, but that also means the high processing cost because we have many data points that we need to take care of in our computer. Right. Here this is simple. We have just edges on the edges of this cube, but the more edges and vertices we get, the more data we have to handle. Yeah, so here we start with a vertex set, then we could do tessellation using an algorithm. Later we come to the description of those algorithms. And then when we have this object, then we can do the so-called shading, which means we turn on artificial or simulated light. Yeah, so here's the triangulation. So a simple polygon can be subdivided by triangulation, which you can see here. So basically we have an object and we subdivide it into triangles. So if we have n corners, it can be divided into n-1 triangles. So it can also be shown that triangulation of a polygon with a complexity of order of n is possible, which means it's proportional to the number of corners. So that's actually quite good. Yeah, advantages and disadvantages of polygons. So the advantages are that they are well suited for flat surfaces, right? Because triangles or polygons are flat. And arbitrarily exact approximation is possible depending on the polygon number. We have simple processing algorithms for them, and they are directly supported in hardware, for instance the GPU. Disadvantages are that we have geometric alias effects. The accuracy depends on the scaling. So that means, for instance, we sample a surface, and if the surface is represented by not enough triangles, then we might get aliasing effect, as we will see later. And curved surfaces, round surfaces, can only be approximated by piecewise linear approximation. That means we need high memory requirements for well-approximated curved surfaces. And also a direct manipulation of approximated surfaces is difficult and complex because it affects many of those points and triangles. Yeah, and that leads us to points and parametric representations or curves. So here about the parametric representations of lines and surfaces. We want to have an exact description of curved shapes, which is easier to manipulate using weights and tangents. And this also should lead to reduced memory requirements. But it also means more complex processing and no direct rendering, because it's an indirect representation. So there are different forms of representation. First, the explicit functional form. It's like a function, right? So we have coefficient y depends on coefficients x using some function f. Right? For instance, f is 5x plus 7. So we start with, say in the two-dimensional case, with coordinate x, and then the coordinate y is computed from the coordinate x. Right? So it's like the usual form. You have a plot x and y. Y is usually the function value, and x is the independent variable, the input of the function. So in this way we get a two-dimensional function. And then we have the implicit form. So here the two coordinates x and y are treated equally. like we actually prefer in computer graphics, right? We don't need to distinguish between dependent and independent variable. We just treat them equally. And we have hence a function depending on the two coefficients x and y, two coefficients or coordinates x and y. For instance, here the function x squared plus y squared equals 1. And when you remember trigonometry, then this describes a circle of radius 1, right? So you can then also bring the 1 on the other side. Then we have x squared plus y squared minus 1 equals 0. And this is solved by all points which lie on the circle around the origin with radius 1. Right? So this is also a way to describe a 3D object, or in this case is a 2D object. We can also add a third coordinate z, and then we would have a sphere, right? X squared plus y squared plus z squared equals 1. Then we get a sphere of radius 1, which fulfills this equation. Yeah, then we have the so-called parametric shape. So here we have a function of a helper variable t, or rather a function for each coordinate x, y, and perhaps z. So here's a function x of t, y of t, and in 3D we would have a z of t. Right? This would then describe an object. So this is also kind of a mapping of this one-dimensional helper variable t. T usually goes from 0 to 1 to a two-dimensional or three-dimensional space. So here in this case is an example where we would then map this one-dimensional t function, t variable, which goes say from 0 to 1, to a part of a circle, right? Here cosine and sine describes pieces of a circle in 2D, where the cosine describes the x coordinate and the sine describes the y coordinate. And if this t actually goes from 0 to 2 pi, where 2 pi is 360 degrees in radians, then we would have a complete circle. So observe that if you have cosine and sine in computing languages or programming languages like Python, then they assume the angle in radians. So the argument of the cosine and sine is always in radians, which means 360 degrees is 2 pi, 180 degrees is pi, and 90 degrees is pi over 2. Right? So that's something to keep in mind. So that's different from your pocket calculator. Yeah. So here we have examples. First, the functional form. So this is basically how you plot a function. Here's a function of one variable, and here's a function of two variables. So the f would be the z, the third coordinate in this case. Here's again the implicit form. Here this would be the description of a circle with radius 1, the center of the coordinate origin, and here is the parametric form. Yeah, so for the explicit representation we have only one y variable for each x value. So that means there are no curves with vertical tangents possible, which means several y values for one x value. Right? So that's the problem. It depends on the coordinate axis. And that also means it's not invariant to rotation, which is bad for computer graphics. So that's not so good. Second case, implicit representation form. This has the disadvantage that equations can have more solutions than wanted, which requires boundary conditions. We have a complex evaluation of the equations, and tangents are difficult to determine. The advantages are we have a simple segmentation of the space, well, I should say space, not room. So space. So inside our object is the function where the function is smaller than 0. Outside of our object is where the function is larger than 0, and the surface is where it's exactly 0. So this way we can easily distinguish between inside and outside and on the surface. Therefore, this is convenient for constructive solid geometry. And we have a simple cutting and distance calculation. Yeah, then we have the parametric representation form. Here we have no ambiguities because we just have functions for each of the coordinate values. Any multi-dimensional curve shape is possible, and it's invariant to rotations. Right? That means the parametric representation is most commonly used in computer graphics. So having a function for each coordinate value is the most convenient representation. The curve can be drawn by variation of the parameters, like the t that we just saw. So this gives us a curve in 2D or 3D. If we have two helper variables like u and v, then we can have a surface in 3D. Yeah, also derivatives are easy to form because we can easily compute the derivative of those functions. And the piecewise definition of complex shapes is also possible. So where we can basically append piecewise surface patches. Yeah, here's a simple example for the parametric form, a Python OpenGL example. So this is also made such that you can try it on your own computer. So now you can actually test if you can get it run on your own computer. All the programs I show here are in Moodle 2. You can download it and test it on your computer. Right. So we use the parametric form to draw a circle. No, first we use it to draw a line. So next is a circle. So here's the line. And in OpenGL, this is done with GL line strip to draw the lines. And GL vertex 3f, 3 means 3D and f means float values for the argument to specify the vertices. So here in the argument, I put the vertices and then it draws me the line between them. To draw a circle with trigonometric functions, we draw in the plane z equals 0 with argument f between 0 and 2 pi. So now comes the circle. So here we make those points, x and y, and then we connect those points with our vertices. Right, you can see it. So here I define the points, the edges, using our trigonometric functions. So here the cosine for x and the sine for y. The third dimension would be z, but since we just look at a plane here, we just set it to 0. So here this is on the plane z equals 0. But in general, you could also add some value here, some other value here. And then it's in this program. Let me open this program. Line strip Kreis. So it means line strip circle. Copy. And I open my terminal. So this terminal is now where I have all my Python examples. And so you also need to create a directory with the Python example that you want to run. Right? So you go with your terminal to this directory. You can check if your example is there by using ls for list. Right? So this is the command for listing everything inside this directory, and we can actually see if it has the line, ls line and star.py. So this means it lists everything that starts with line, then it has some arbitrary characters, and then it ends with .py. Right? And yes, it's there. So that means we can now take a look at it. First gedit line, and now I use tab to autocomplete, ampersand to keep my terminal usable, and then open my editor, which has some other stuff in it. So here you can see it, line strip Kreis. So here it starts with importing OpenGL, different libraries here, and then it defines our display function. So this is the usual way you would do the display of your object. So here you define the projection mode, orthogonal projection here, and you also define the position of the virtual camera. Here is this position in 3D space, and here you define the color, so this should be the background color, and then here you define our vertices for the circle. So you can see it, I have a for loop, right? This f is our helper variable now. So this helper variable now goes from 0 to 2 pi. So you can see here np.py means pi, and np is numpy. You can see here I import numpy as short np, and pi is then the constant defined in this library. So this goes from 0 to 2 pi in 40 steps. Yeah, and then it creates the vertices, the connections between those edges. You can see it. Here we have the cosine, here we have the sine, and we have the 0 for the z variable. And I actually can also include a factor here, as I did. So this is a factor of 1.0. I could also include an offset, which changes the center of the circle, which is 0 here. Yeah, and then I'm done, and here I'm starting it with main part of the program. So here initialize, I'm creating a window of size 640 by 480 pixels, give it a name 3D. Here I define the display mode as RGB. Here I clear the color. Now I give it, I think this is the background, which should be white, and here I'm starting the display function. So now let's try it. So you should do the same on your terminal window, and start it with Python 3 here in my case, and indeed we get a white background and a black circle. And why is it black? Well, because we defined the color here of this object as black. Here this is the object color, turns out to be. And also it's not exactly a circle. So why is it not exactly a circle? It's more like an ellipse. Well, that comes because of our position from which we look at the circle. Remember, this circle is on the plane z equals 0, but now we don't look directly on the circle, but more like from a corner 45 degrees away from it. So that's a perspective distortion. So we look from a little bit off from the side above to the circle, and that's why we get this perspective distortion. So this is actually already doing a 3D projection on our camera. Yeah, and here we can see we have 40 points. We can also reduce the number of points. Instead of 40, we say just take 10. And then you can see that it's actually not exactly round, but a polygon, right? So here you can easily see that it's a polygon, because now we just have 10 vertices here, right? 10 points, 10 vertices. So it only appears round because we have enough of those vertices. So here, going back to 40, you don't see the individual points anymore. Yeah, and this also shows that it depends on how you project it. If the object appears small, far away, you need fewer points, fewer vertices, and if you're closer up, you need more. So it depends on how it's projected on your virtual camera. Yeah, so this is what we saw. We get a circle distorted in perspective. The more support points or edges or vertices we use, for angle F. Which means more vertices in space, the rounder it appears. Yeah, so going back to the slides. Yeah, we can also display only the calculated vertices of the circle without the connecting edges by using GL points, right? So now I can go back to my editor. So here I have vertex, and instead of vertex I can use here. So here we have, instead of GL line strip, I can use GL points and give it a certain size. For instance, here point size 5. So here we define the object, line strip, and alternatively here the points. And here in the for loop, for each case I define the vertices. Right. So this is actually what OpenGL memorizes. Basically, we collect the vertices here for the object that we defined here, or initialize here. So let's start that again. So line strip. Yeah, now you can see we have those 40 vertices. Right? Without the lines that connect them, you can now actually see that it's just 40 points, 40 vertices in space, and that is actually a polygon instead of a circle. Right, so that makes it clear. Yeah, so now I can go back to the line strip. And you can see that it's a nice round circle again. Okay. Yeah, so here we used cosine and sine to generate the circle line. But in general, we don't want to look for mathematical function for our objects, but we want to have some universal way of building curved objects. Right? We don't want to care if it's a circle or ellipse or something else. We just want to have building blocks for building our rounded objects. And those building blocks are offered by polynomials. Right, so here you can see it. Those polynomials have the advantage that basically you can stop at some point. So here you have k, so you have the choice of how curvy it becomes. And then you determine the shape of the curve by using the coefficients p. Right, so here you can actually approximate any curve if you have high enough order, which is determined by the highest exponent here. So we call this degree k. And actually the Taylor the Taylor expansion lets us tells us how to choose those coefficients for any desired shape. So the Taylor expansion tells us that polynomials can be used to approximate any shape we want, and even gives us the p's. Actually, we want to do it simpler. We don't want to apply Taylor, as we will see. We can actually do it even more simple for the case of computer graphics. Yeah, PI determine the form of the curve, the shape. They depend on the shape of the curve. Yeah, so we have the degree K, but in computer graphics, it's usually K equals 3, a cubic function. So that's quite simple. We just go up to the third power. And this gives us a compromise between the control possibility and the computing effort for the computer. Yeah, this provides a control over endpoints and the gradient. So when we have K equals 1, this is just a linear function, like a polygon edge. If you have K equals 2, so now I have this point, now it becomes curvy, right? Because it's like a parabola. Then it's like a square function parabola or a conic section. And for K larger than 3, we have an increased tendency to oscillations because of this high exponent, since the curve can have up to K minus 1 turning points, and that could become a numerical problem. So that's why K equals 3 is a good compromise. Yeah, so the important property of curves is the continuity. We want to have curves which are smooth. So important for the smooth, well, I should call this interconnection. Of curve segments is that we have a section by section definition of curves and surfaces. So we want them to have a connecting point which also has this smooth property. So we want to avoid jumps in the geometry, because that would lead to visible edges during shading and would result in sudden movements at motion path. So if we use that for animation. Yeah, and this condition also applies to areas, not just curves. So we define the smoothness by C continuity, right? This is the correspondence of the nth derivative at the connection point of two curves. Yeah, I should say continuity. Yeah, so this should mean continuity of the nth derivative at the connection points. So that means if we have the C0 continuity, we have a position continuity. That means we have no jumps where two curves are supposed to connect, right? So the curve is more or less continuous, but it's actually continuous. So position continuity. So that's the least we want to expect. Then C1 means tangential continuity. That means the first derivative is continuous, right? The tangent of two curves which meet are pointing in the same direction. So the end vectors, the gradients, are parallel. Transition between two segments without an edge. So otherwise we would have a sharp edge at that point. And to avoid this sharp edge, we define the C2 continuity, which means we have a curvature continuity. The amount of the edge vectors or the gradients is equal on both sides. So I should say on both sides. Yeah, and here it's the magnitude of the gradients at the ends. Yeah, so we get a smooth transition with the same rounding between two segments. Here the change, because we have a derivative of the gradients. Yeah, in general we say that a curve is Cn continuous if all of its derivatives up to n match across on the curve pieces. Yeah, there's also the G continuity, which refers to the geometric continuity. So this no longer includes a speed of the parametrization. For instance, if we have cosine and sine of t, we could have a t or a constant times a t. So that would influence the derivatives, but not really the geometry. So the G continuity tries to get rid of this dependency of the parametrization on this factor. But except for that, it's the same meaning. It's just more meaningful for computer graphics. Yeah, so we basically use both interchangeably here. So here you can see examples. Here you have C0 continuity, which means two line strips, they meet here at the same point, but the derivative is different, right? Different derivatives, that's why we have a sharp edge here. Then we have the C1 continuity. So here the derivatives are the same for both curve pieces, and here also the amount of curvature here is the same. So you can see this is more or less straight, and then here you get a curve. Here you have the same curve on both sides. So this is the C2, and similar for G1 and G2. Same curvature on both sides. Yeah. So polynomial coefficients are not well suited for well, waveform or shape control. Shouldn't really call it curve. So the coefficients are not so obvious, right? When we have a polynomial, the meaning of P is can be extracted from the Taylor expansion, but it's not so obvious for designers of graphics, of 3D graphics. So that's why we use the representation as the sum of basis functions, right? Or basic functions. So that means our curve is constructed by a weighted sum, and the weighted sum has control points in it. Right, so here the b's are our basis functions, and then p, this is actually a vector, which is the control points, or which are the control points. So p is a three-dimensional vector which contains the coordinates of our control points. And this actually gives a better meaning to the resulting curve Q of u. Right? Q is again containing the three dimensions, x, y, and z. That's the output of this function Q. U is our one-dimensional input, usually between 0 and 1. And b is now our polynomial. And we can see here we have now k plus 1 control points and the same number of different polynomials, bi. Right, and maybe I should call this basis functions here. Yeah, so these are scalar fixed basis functions. So these bi are given, they are fixed, and that's why they are called basis functions. And they are such that they are greater than or equal to 0. And are linear independent polynomials whose sum results always in 1. So for each u, the sum of all those polynomials is 1. And this is a kind of modular system with basis functions as building blocks. Right. And this means the sum produces a variable weighted mean value of the control points. So if the sum of the b's is always 1, then this is kind of a weighted average of those control points. So that can be seen here in the next plot or picture. So here we have, for instance, 3 control points, P1, P2, P3. Here in this example, it's 2-dimensional. We have x and y coordinates. And then we can compute a curve in 2D by using this sum here. So here in this case, the sum goes up to, actually starts at 1 and goes up to 3 in this case. And so it contains 3 of those polynomials. So here important is that the sum of those polynomials for each value of u is always 1. So maybe I can actually add this argument. Sum b sub I of u is always 1, independent of u. And that means we are always inside this triangle which is spanned between those 3 points, right? Any weighted average between, say, P1 and P3 is on the line connecting them. And the same for weighted averages between this average and P2 is a point in between. So that means if this is true, if the sum is always 1 and each b is larger than 0, then the resulting points must be within the spanned triangle. Right? So for any u, we get a point inside. For instance, the center point is obtained by all bi's being 1/3. So 1/3 P1 plus 1/3 P3 plus 1/3 P2 gives us exactly the center point of this triangle. If we have different weights, then we get different points. For instance, this point here for u equals 0, and then if we vary u, then we change the b's and maybe we end up here in the center. Right? And what we get is a smooth curve like this, depending on our polynomials. Right, so that's convenient. So basically we have building blocks, and those building blocks are our control points and the polynomials. Yeah, and here you can see how you could do it in OpenGL, Python OpenGL. So we would use again our GL points. We would define our vertices, and then the interpolation is done in this Python function .interp.py. So let me open it to see what's inside. So gedit. So here you can now see what's inside. So it's actually quite similar to what we had before. We have our projection. Then we have our virtual camera. And here we have the control points. So this is P0. So now instead of using the cosine and the sine function, I directly define it by the coordinates. So here the P0 is now a NumPy matrix with those coordinate points. Right here, P1 and P2. So 3 different points in 3D. Again, look at the third dimension, z, which is always 0. So again, we are on the plane z equals 0. Then here, the object color is black, all zeros. And now we do the interpolation here. Right, so I define 3 polynomials. So these are now actually some fantasy polynomials which have this property that they add up to 1. Right here, b0 is u square, b1 is 0.3 minus 0.3 times u square, and b2 is 0.7 minus 0.7 times u square. So here we can print the values. You can see there's a for loop, and I let the helper variable u vary between 0.1 and 0.9 in 10 steps. So we will get 10 values for the b's, and each time they should add up to 1, which we should see here in this print command. Yeah, and then we can plot the resulting interpolated points. So here we can see it. So we have the first control point P0 times B0, then we have B1 times P1 plus B2 times P2. Right, so this is now again a NumPy matrix containing 3 coordinates, 3 coordinate values, and this is then the argument for vertex 3f, v for vector. So this then memorizes those vertices from the for loop and gives it to our object. Yeah, and then we should see our object as points. So you can see we have points with point size 5. So we should see those 10 points on the Z surface. So let's take a look. Python 3. Yeah, so here you can see the original control points in red. So let's see, where do I have them in red? Yeah, so here again I create the window, and here are the 3 points. Oh, interesting. Where do I have them in red? Okay, in any case, these are the 3 original control points, P0, P1, P2, and these are the interpolated ones, right? You can see here they actually move from this one edge and go up to on the edge of these 2 control points. So it just moves up. So here it's not really curved, it's a straight line, but it's nice smooth, right? So that works. Okay. Yeah, and we should also take a look at the output of this function. Here you can see it. So here you can see the obtained points, and here are the sums of those factors. Right, so here you can see when you compare it. So the print here, the first print gives us the individual factors here. Here these are the individual factors bi, b0, b1, b2, and then the sum of the 3. So you can see those 3, they always add up to 1, no matter what we choose for u. So it's always a 1. But you can see here their contributions change. So in the beginning, the first factor b0 is smallest, and the end it's the largest. Right, and the others change accordingly. Yeah, here's the last one. So here the first one is now the biggest, and the middle one is the smallest. Yeah, so that worked. So the sum of the factors, as they are displayed, is always 1, and the interpolated points lie in the triangle drawn by the 3 red origin points, the control points, the convex hull. Yeah. Okay. Yeah, and that leads me to the end of this lecture. So go ahead, try out these functions yourself and maybe experiment a little to see what happens. How you can maybe change the shape of the curve or use different control points and see how things are changing. Okay, then thanks for your attention and see you next time.